All right. Hey, everybody. Um, so in this video, I want to continue working through chapter 6. We've been talking a lot about how to, discuss and look at the limit of a function. And I want to move on to our next big topic, which is continuity and what it means for a function to be continuous at a given point. So I want to start just by introducing the definition of continuity. And I want to compare this definition with the definition of limit. So up here we have the definition of a limit. This is what we learned about last time. So if we take a function f and we take a point p that's an accumulation point of the domain, we say that a function f has a limit at p if and only if, and now here's the meat of the definition, for all epsilon greater than 0, there exists a delta greater than 0 such that whenever we then look at a point x that is in the domain and within a distance delta of p, we have f of x minus L is less than epsilon, right? So f of x is within a distance epsilon of L. And this is the notation that we used. Now, let's compare that definition to what it means for a function to be continuous at a point p. We say a function is continuous at a point p if and only if, for all epsilon, there exists a delta such that whenever x is a point in the domain and x minus p is less than delta, we have f of x minus f of p is less than epsilon. And so this is the definition that we'll be working off of for continuity. And I want to start just by pointing out the major differences between these two definitions, because there are a lot of similarities, as you've noticed. Difference number one is this final piece of the statement, right? So up here, we're talking about the limit of a function, and we're saying that whenever x minus p is within distance delta, or whenever x minus p is less than delta, so whenever x is within a distance delta of p, we have f of x minus this limit L is less than epsilon. And so we're talking about our y values or our function values getting very close to our limit L. Down here in our definition of continuity, we're talking about our f of x values, our y values, getting very, very close to f of p, the output that's associated with the point p. So no longer just a limit, but specifically the output of the function at the point p. That's big difference number one. Big difference number two is that up here we have this 0 less than x minus p less than delta, while down here we are missing that extra piece, right? So the major difference there is that in this top statement, when we're just talking about limits, we do not want to allow x to actually equal p, right? Because we want the possibility to exist that our function is not even defined at p, or we want our function to be defined radically differently at p. And so up here, we don't actually want to consider what's happening at x equals p. That's not true in the case down here, right? So down here, we're just saying that we're taking any x value that satisfies x minus p less than delta. And that could possibly include, in fact, it should include p itself, right? Because p minus p is 0, which is certainly less than delta. So the major difference between these two definitions are sort of summarized in these two points right here. And because those are the only real differences, we can see that the structure of continuity, in particular, the for all epsilon, there exists a delta, such that whenever distance is less than delta, we have output distance is less than epsilon, right? That really suggests that this continuity definition is secretly a limit definition, or at least they're very, very closely tied together. And that is absolutely true. What we see is, in fact, that the definition of continuity really is a definition about limits. Indeed, if I assume that my function actually exists at p, that p is a point in my domain, and if I were to change my limit L to an expression f of p, right, then I can sort of look through the definition up here and get an f of p. And if my function is defined at f of p, we notice that this final piece, that will be satisfied always at p itself, right? So we can actually get rid of this piece right here. So all of that is to say that if our function is defined at p, and if f of p is actually the limit in question, then there really isn't a difference between these two definitions. And the content of that idea is summarized in lemma 6.12 from the text, right? Lemma 6.12, which says that our function is continuous at p and it satisfies this definition if and only if the limit as x goes to p of f of x is actually f of p. So it turns out that the definition of a function being continuous, so all of this, that is true if and only if this statement is true right here. And that's true exactly for the reasons that we've discussed, because if we define the limit as x goes to p of f of x as being equal to f of p, then this statement right here will reduce all the way down to, or I should say will be equivalent to this statement up here. And so in fact, these two expressions are functionally the same as given in lemma, what did we just say? 6.12. So in a Calc 1 class, this is probably the definition that I would give my Calc 1 students, right? And then I would say something a little hand-wavy about how this makes it so that you can draw a function without picking up your pencil or something like that. And I would talk a little more about it. But we know in the world of real analysis, we can have weirder functions where weirder things happen. And so this is really going to be the rigorous definition of continuity that we use. And it's 6.12 that really allows us to draw this connection between the two.